In this example, we will integrate arctangent of x. Now, at first glance, this does not appear to be well suited for integration by parts. And the reason I say this is recall the integration by parts formula. The integral of u dv is equal to uv minus the integral of v du. So the idea is that we apply integration by parts to a product where we can pick the function that's going to play the role of the u and the other function which is going to play the role of dv. But the observation to make here is that when we go to integrate arctangent of x, we could rewrite this so that it is a product. One thing that's implicitly always hiding here is that we can write this as tangent x times the function 1. And now we very clearly see where we have two functions. We have the arctangent, and then we have the 1. Now, when we apply integration by parts, whatever function that we pick to play the role of dv needs to be something that we can anti-differentiate. So arctangent would not be a good choice, right? If we knew the integral of arctangent, we wouldn't need integration by parts. So we're going to let dv be the 1, so that the v is x, and that leaves u to be arctangent. But the good thing is that arctangent is a derivative that we know. It's 1 over 1 plus x squared. So integration by parts tells us uv, so x arctangent, minus the integral of v du, so minus the integral of x over 1 plus x squared dx. Now, recall what integration by parts does for us. It takes this difficult integral we started with, and it expresses it in terms of this simpler, easier to evaluate integral. And for this new integral, we see that you have this function derivative pair appearing, and u substitution might be jumping out at us. You have maybe what we'll call a w in the bottom since we've already used u. So we'll say w is 1 plus x squared, so that dw is 2x dx, and more specifically, 1/2 dw is x dx. So the x dx in the top is going to become a 1/2 dw, the 1 plus x squared on the bottom is going to be w. So the x arctangent x comes down for the ride. Now, one thing to keep in mind is that we're going to use proper notation. When we write up our answer, it should be mathematics aligned vertically, like we see here, one step down to the next, an equal sign at each step, and we always write that differential, the dx, the dw, as needed. So minus 1/2, which is pulling out front, 1 over w dw. And now we have an extremely reasonable integral left to evaluate. So we have x arctan x minus 1/2 natural log absolute value w plus c. And since we've done a substitution, our last step here is to resubstitute to get it back in terms of that original function. So this will be x arctangent of x minus 1/2 natural log absolute value 1 plus x squared plus c. And a quick observation to make here is that this technique can be applied to other inverse functions as well. So it could be used to integrate things like arc cosine, arc sine, or even something like, say, the natural log of x.